Welcome to homogeneous linear nth order ODEs. So recall a homogeneous linear nth order ODE takes the form nth derivative of y plus p1 of x times the n minus first derivative of y plus all the way through p sub n of x times y equals 0. For notational sake, we'll let Ly be equal to that left-hand side. And so the equation becomes Ly equals 0. Just a quick note, just like we had for second order, Ly is a linear operator. Since derivatives are linear operators, and we wind up getting that if y1 through yk are solutions to Ly equals 0, then so is any linear combination. So then so is y equals c1 times y1 plus all the way through ck times yk, where c1 through ck are constants. So again, this lends us to precisely what we had for second order. We say y1 through yn form a fundamental set of solutions to the nth order equation Ly equals 0. So we say y1 through yn form a fundamental set of solutions to the nth order equation Ly equals 0 if the following two things are true. So if, first up, y1 through yn are solutions to Ly equals 0, and second, y1 through yn span the solution set. So in other words, every solution can be written in the form y equals c1 y1 plus cn yn for c1 through cn constant. So just like before, we call this y equals c1 y1 plus all the way up through cn yn the general solution. So this linear combination of the y1s is called the general solution. Again, this is just an expansion of what we had previously. The key thing here is that the n's have to match. So the y sub n and the nth order, those are referring to the same n. This way we form a basis instead of just spanning and going over what we need. We get a quick theorem which says that solutions y1 through yn to the nth order Ly equals 0 form a fundamental set of solutions to Ly equals 0 if and only if the y1 through yn are linearly independent. Here, linearly independent is the same linearly independent we are used to seeing in linear algebra. So this means that C1y1 plus CN equals 0 happens only when C1 through Cn are equal to 0. So this sort of lends us somewhat into what we're looking at. The Wronskian will give us a little more detail. So recall when we were doing second order, we had a Wronskian, which wound up being the determinant of the matrix y1, y2 in the first row and y1 prime, y2 prime in the second row. We have a very similar thing here. So note that if y1 through yn form a fundamental set of solutions, on some interval AB, then every IVP with Ly equaling 0 as its equation and y of x naught equaling k naught all the way up through n minus first derivative of y evaluated at x naught equaling k sub n minus 1. Every IVP has a solution, so every IVP must have solution of this form. So must have solution, and in fact, a unique solution if our conditions are met, of the form y equals C1 y1 plus all the way through plus Cn yn. So what this means then is that then the system of equations, which is C1 y1 of x naught plus all the way through Cn yn of x naught. That is just y of x naught, so that should be equal to k naught. All the way through C1 y1 n minus first derivative evaluated at x naught plus all the way through Cn times the n minus first derivative of Yn, evaluated at x0, equals k sub n minus 1. This system has a unique solution. Then writing this system with matrices, we have then the equation y1 of x0 through yn of x0 as our first row, and then all the way down to y1 n minus first derivative of y1 of x0 through the n minus first derivative of yn evaluated at x0. This times the vector c1 through cn equaling the vector k0 through kn minus 1 has a unique solution. And this is only true if the determinant of that matrix is non-zero. Then the determinant of that matrix, which we will define to be the Wronskian. So then the determinant of the matrix does not equal 0. And so we call this the determinant of the matrix, our Wronskian. And in particular, this is evaluated at x0. So we get a little theorem. This kind of, again, sort of showing where the Wronskian came from, kind of sort of previews the theorem. What we have is that if y1 through yn are solutions to the nth order equation, really nth order linear equation, we'll stick with that. Ly equals 0. And Ly equals 0 is normal on AB. Again, that simply means it satisfies the conditions of the existence and uniqueness theorem. Then the following statements are equivalent. So first up is that y1 through yn form a fundamental set of solutions to Ly equals 0 on AB. Second is that y1 through yn are linearly independent on AB. Third is that the Wronskian of y1 through yn is nowhere 0 on AB. So notation wise, we denote this as W of y1 through yn. So this Wronskian is non-zero on AB. And then the most useful piece here is we actually just need the Wronskian to be non-zero somewhere on AB. So this is very, very useful to us. I'm going to actually change that to somewhere in AB. Again, this fact is very useful. This means that in order to check for a fundamental set of solutions, we just need to check the Wronskian as non-zero somewhere. So in order to check for a fundamental set of solutions, we just need to check the Wronskian at one point. So we will be having to do plenty of determinants and matrices. This is going to be a 4x4 matrix in our example here, but this is useful in that we can get rid of our x's. So let's go ahead and look at the example. I claim that y1 equals e to the x, y2 equals x e to the x, y3 equals e to the 2x, and y4 equals e to the negative 2x are all solutions to the equation fourth derivative of y minus 2 times the third derivative of y minus 3 times the second derivative of y plus 8 times y prime minus 4y is equal to 0. Our job is to verify that they form a fundamental set of solutions. So we know that the Wronskian of y1 through y4 is equal to the determinant of y1, y2, y3, y4 across the top. So we have e to the x, x e to the x, e to the 2x, and e to the negative 2x across the top. And then we have derivatives. That first column will go e to the x, e to the x, e to the x, all the way down. That second column, we would have an x e to the x plus e to the x. Then we would get x e to the x plus 2e to the x and x e to the x plus 3e to the x. I'm going to shift over those right two columns a little so that e to the 2x, we would go to 2e to the 2x derivative, then 4e to the 2x, and 8e to the 2x. In that last column, we would have negative 2e to the negative 2x, 4e to the negative 2x, and negative 8e to the negative 2x. Now, I don't want to work with all these x's. The theorem we were just working with told us we could look at a specific point. Constant coefficient equations set equal to 0 are going to be normal everywhere. So we can pick at any point. That's why I didn't specify an interval. So this is normal everywhere. So it's normal on negative infinity to infinity. So let's just go ahead and pick x naught to be 0. So we are actually just going to take the Wronskian at 0. So the Wronskian, so picking x equals 0 as our test point. we have then the Wronskian of y1 through y4, evaluated at 0, is that first column, if we evaluate it at 0, e to the x is just 1. So we just have a column of 4 ones. That second column, all of the x e to the x's will go to 0. So we'll have 0, 1, 2, 3. Third column, e to the 2x is just 1, or e to the 2 times 0 is just 1. So we will have 1, 2, 4, and 8. And then that last column, e to the negative 2x, is again just going to be 1. So we will have 1, negative 2, 4, and negative 8. This makes our life a little bit easier. We no longer have to worry about those x's. We can go ahead and just take this determinant. Rule for the determinant, we can pick any row or column to work with. I might as well just work with that first row. We have 1 times the determinant of the matrix ignoring the first row and first column. So we would have 1, 2, negative 2, 2, 4, 4, 3, 8, negative 8. Then we subtract off 0. That's the second position in the first row, times the matrix where we eliminate the first row and second column. So we will multiply by 1, 1, 1, 2, 4, 8, negative 2, 4, negative 8, going down those columns. Then we have plus 1 times the determinant of the matrix where we eliminate the first row and third column. So we'd have plus 1 times 1, 1, 1, 1, 2, 3, and negative 2, 4, negative 8. And then we will subtract off that last position as 1, and we will multiply by the determinant of the matrix where we eliminate the first row and fourth column. So we'll have minus 1 times the determinant of 1, 1, 1, 1, 2, 3, and 2, 4, 8 as our columns. Little shortcut for determinants of 3 by 3 matrices. We can just copy the first 2 columns off to the right. So we'll copy 1, 2, 3, and 2, 4, 8 here. Then we look at the diagonals. We add all of the rightward diagonals products, and we subtract all of the backwards diagonals. So this first one we are looking at, we have 1 times 4 times negative 8 is negative 32. Then we will add 2 times 4 times 3. So we are looking at plus 24. Then we will add negative 2 times 2 times 8. And we are looking at another minus 32. Then we will subtract off negative 2 times 4 times 3. So that becomes plus another 24. We will subtract off 1 times 4 times 8. That becomes another negative 32. And we will subtract off 2 times 2 times negative 8. That becomes a plus 32. So 2 of those 32s cancel each other out. Negative 32 plus 24 is negative 8. And then we have another negative 32 plus 24. So we have another negative 8. This should be negative 16 as our final answer. This next one we can ignore since we're multiplying by 0. Then 1, 1, 1, 1, 2, 3, and negative 2, 4, negative 8. Again, copying that right-hand side, or copying the first two columns to the right, we have 1, 1, 1, and -2, 4, -8. Our forwards diagonals, we are looking at positive, add them on. Our backwards diagonals, we subtract off. And we wind up with 1 times 2 times -8 is -16. Then we have +1 times 4 times 1, so +4. And we have plus -2 times 1 times -8 becomes +16. Then we are subtracting off -2 times 2 times 1, so we are adding another 4. We subtract off 1 times 4 times 3, so -12. And subtract off -2 times 1 times -8, that becomes -16. Putting this all together, +16 and -16 cancel each other out. We're looking at -16 plus 4 is -12, plus 4 is -8, -12 would be -20. And then the last one we need, again, copy that first two columns and to the right. So we have 1, 1, 1 and 1, 2, 3 copied to the right. We are going to add the 4 diagonals and subtract the backward diagonals. And we are looking at 1 times 2 times 8 is a +16, plus 1 times 4 times 1 is +4, plus 2 times 1 times 3 is +6. And we have -2 times 2 times 1, -4, -1 times 4 times 3 is -12. And -1 times 1 times 8, oops, sorry about that, is -8. So we are looking at 16 plus the +4 and -4 cancel out. So we are looking at 16 plus 6 is 22, -12 is 10, -8 is 2, assuming I did my arithmetic correctly there. And so our Wronskian of y1 through y4 evaluated at 0. We are, sorry, evaluated at 0, not equal 0. We are looking at, we have 1 times -16 plus 0 plus 1 times -20, and then we have -1 times 2. So we are looking at -16 minus 20 minus 2 becomes -38, which is definitely not equal to 0. And so we have a fundamental set of solutions. So y1 through y4 form a fundamental set of solutions. As you can see, if we have a fourth order differential equation, checking the Wronskian can be quite annoying. Similarly, solving a fourth order equation, we will be working with matrices, finding Wronskians. So you do want to become comfortable with taking determinants of matrices. Once you're comfortable with them, you are welcome to use technology instead.